Okay, chapter 5 is called Fundamental Prototypes of Tropical Systems. Essentially, we looked at the wave kinematics in chapter 4. We looked at how background state can modulate the wave modes and have implications for energy dispersion, which is obviously very critical for dynamics of the atmosphere and oceans. To make that into a physics, we obviously need to look at the tropical system. So here we'll run through some equations which are pretty hairy, so we won't derive all of them. We'll try to keep our head clear about what the equations are so that when we come to the physics, they make much more sense. Here it's just a dry run through the equations with some physics, but they are kind of complicated. So we'll just look at them, get comfortable with them so that when the physics comes, we can recall and look again at all the terms that we are looking at here. Okay, the Laplace shallow fluid system, he was basically trying to learn about tides. So he made some assumptions: a spherical shallow fluid of depth h, incompressible, so no density effects, density variation effects, rotation 2 pi per day or omega per second, and it can be used to build a shallow water ocean system, which can be then applied to the real ocean and the atmosphere, and then we'll make a stratified atmosphere system to see how the vertical modes and the horizontal modes and the scales are all intimately tied together. So, as I said, we need to just get comfortable with it despite their complications. This is the way Laplace saw the shallow fluid system. Basically, he's looking at a section here of a ocean, A, B, C, D. So you're going at the bottom from A to D, and then at the top from B to C on a rotating Earth. And you have bottom topography, which is given as a distribution of latitude and longitude. And he's assuming a meridional gradient in sea surface height going down from low latitudes to high latitudes, or lower latitude to higher latitude. By now you are comfortable with the idea of geostrophy. So if you have a slope going down this way, then you have a flow, geostrophic flow going into the page. So you have the arrow's tail here. So that gives us the mean background geostrophic state. You have the mean surface given by h bar here, which we think of as equivalent depth, and you have dynamics driving, let's say in his case the tides, driving this surface sea surface height variation, hxyt or lambda phi t, and then we translate that into equations. Okay, let me make sure I read everything. Mean depth is h bar in meters. Zonal flow is geostrophic u phi in balance with this hs surface slope. Potential phi will come to in a minute. So perturbation displacement of the surface hxyt or h lambda phi t is going to be looked at in terms of the equations. This is the simple form of his equations. You can see the geometrical terms have been dropped. So du dt, which is the substantial or total derivative, minus f times v plus 1 over a cosine phi partial of gh minus phi, the potential with respect to longitude. So when you have the longitudinal and latitudinal variations of the potential, it's going to perturb the mass, center of mass of the water column and going to create perturbations, right? That's essentially what this is saying. GH is the fluid, you can think of the height of the mass, center of mass, and then phi is the potential that's going to get term. It's a forcing, basically. So dv dt in the meridional direction plus f times u is 1 over a dgh minus v d phi equal to 0. So we are ignoring the other terms here. And in the vertical, we have dw dt, and then the horizontal divergence equal to mass, which is the heating or cooling, which is a perturbation to the mass field again in the x, y, and time coordinates, right? The first thing we will do is restrict ourselves to the tropics and look at the beta plane approximation. Beta, as we remember, is already df dy, only varies in the y direction. So fy at any latitude can be expanded in a Taylor series around its value at the equator, which is 0, plus df dy, which is beta times y, plus other terms. So you can write that approximately as 0 plus beta y, which is just equal to beta y since f at the equator is 0. Okay. We will see in a minute how much error that introduces, this simplification. The value is maximum at the equator because as you go off the equator, f increases and beta decreases. The computation, so here magnitude of beta with latitude, or magnitude of f with latitude, that's the real f here. Beta y has low errors as long as you are in the tropical band, let's say down to something like 25 south, 25 north. Once you go beyond that, you begin to get into errors that become unacceptable, close to 15 to 18 and 20%. Okay, that's this line here. Okay, beta is obviously a kind of restoring force. If you get displaced, planetary vorticity is going to try to restore you, and if beta is strong, that means the equatorial trapping is strong. So if you have a geostrophic velocity in the background, then beta effect is reduced in the sense that relative motion is going to have an impact on how much of a perturbation force beta is. You can do that. You can. We have already said that Coriolis tilts to the right in the northern hemisphere, for example, which is very obvious when you go from south to north because you have the relative eastward velocity which has to decrease, and you cover more distance than the Earth because the radius decreases. You can look up my Coriolis podcast on that. But if you are moving east-west, then you also have this residual force which is going to push you to the right, and that is going to be affected by how fast or how slow you are moving. So, okay, maybe I should do this in the next, but let's look at the height anyways. Define total depth of the fluid and the background state. So h, the height of the fluid, is a function of latitude, longitude, and time because the interface is moving, which is the sum of the mean height that we talked about, plus the slope, plus the perturbations to the free surface, plus the bottom topography. Right? Here, HSV describes the latitudinal slope, as we already saw, which is necessary to support the basic geostrophic velocity on a beta plane. So the balance there is just minus beta y, which is f, times u bar equal to g dhs dy. So meridional pressure gradient is going to give us a zonal velocity, which is what we have already learned. Okay, so let's do this in the next podcast. This is just to orient ourselves in the first podcast, but I think it's clear where we are headed with that, right? It'll become clearer as we get into more and more complicated equations and look at the assumptions we make along the way to simplify the system, to linearize the system, to look for wave solutions, and so on.